So today I'm going to talk to you about everything old is new again, domain-specific languages. How many people recognize Everything Old is New Again as the title of a schmaltzy song? It is. You can look it up on YouTube if you want. I won't inflict it on you now. Okay, are there any questions? Not yet. Okay. Please, I know there's a varied audience here. I know that always, even when I'm not speaking to a varied audience, I can say things that people in the audience don't follow. If you don't understand what I'm saying, please help me out and help the rest of the audience out by asking a question. I'll try it again. Are there any questions? Okay. That's what's on the next slide. How many people have heard the term smuffy? Okay, so smuffy is French for a child's soft toy. And you can see one on my daughter's head. She had many smuffies. That was her favorite. But when she got older, she decided that I needed a smuffy. So she made one for me. So many of you will recognize this as a lambda, the symbol of the lambda calculus. There it is with the pie that she made me later. And the point of doing this is many people tend to think of theory as hard, difficult, all of this lambda stuff that these academics want me to learn to make my life difficult. What I'd like you to take away is that theory is soft and cuddly. Theory is there for you to hug to your bosom at night or to comfort you when you're trying to write a difficult program. And in fact, the theory can give you a very helpful guide often to doing a practical implementation. And that is why the theory is there. Not to make your life difficult, but because it is soft and cuddly. You're taking a picture of the picture. Do you want to take a picture of the thingy? Okay. So the question I'm going to be looking at today is, how does one integrate a domain-specific language and a host language? And I'm going to go back to two old ideas, right? The old idea of quotation from Lisp, originally due to John McCarthy in the 1960s, and the even older idea of normalizing or simplifying proofs due to Genson in 1935. Prague has the distinction of being the city that killed Genson off. He was a Nazi. He was teaching here when the Russians rolled in. They put him in prison. They didn't feed him or the other prisoners. He died very young. So let's get started. So for most of this, I'm going to look at one example, which is embedding SQL in F# as a domain-specific language. And at the end, I'll say a little bit also about embedding Feldspar in Haskell. So Feldspar is an embedded domain-specific language in Haskell. And we've been testing out our techniques. Can we duplicate what they did using our techniques? And the answer so far seems to be yes. So we've got two examples so far, but I hope that after you've gone through this, you'll think, yeah, that's a technique that might be useful in certain circumstances. Maybe I'll try it out for mine. And domain-specific languages can mean many things, but in particular, I'm going to be focused on those where you have some host language, say F# or Haskell, and then you have a target language, say SQL or C. And you're trying to write a nice F# or Haskell program, and then that actually stands for generating the equivalent SQL or C. So I'm going to be looking at SQL mainly. So here's a little database of people, and here's a query that we can run over that. So from people bound to U, and from people also bound to V. If the U's name is Alex, and V's age is less than U age, then select V name as name and V age as age. And you get that table over there. Those are all the people who are younger than Alex. Okay? Any questions about that? You can nod if that is completely boring. Nobody is nodding. Now, what we want to do is look at our database within our programming language, in this case, F#. So we can just easily take a database and convert it into data in our programming language. So here's an example of a database. So it's a record, with one field, people, corresponding to the one table in the database. And then that is bound to a list, and the list has a bunch of records, and each record has one field for the name column and one field for the age column. And I've used lists here rather than bags because that fits well with F#, which supports a list type rather than a bag type, but we won't care about the ordering of the elements in our list. Okay, so this is completely straightforward, right? And we could add a little construct to our programming language, database, which reads in the database and turns it into data in the form that I just showed you. And then we could take our query and just rewrite it out. So to find all the use, so this is going to return a list of records where each record has a name field and an age field. There we are. And again, we just iterate for each U in the people table and for each V in the people table. If U's name is Alex and V's age is less than U's age, then return a record with a name field and an age field taken from V. So again, this is pretty straightforward, and I hope the correspondence to the query I showed you before is pretty straightforward. Now, I've put primes on these things. And within this talk, prime is going to have the following meaning. I wouldn't do that if I were you. Why have I put primes here? Does somebody want to suggest? Yes? Right, so we run over everybody in people once, and then we run over them again. So if people has n entries, this will take time n squared. Whereas the SQL query I showed you before, if you use indexes properly, just runs in linear time. So that's one thing that's wrong. It takes too long. Anything else? Yep?
You don't load the database into memory?
Right, so the example I showed you, the database had only 6 entries. Reading that into memory is not a problem. Of course, databases can contain terabytes of data, and then reading all of that into memory would be a problem. So it uses too much space and too much time. But other than that, it's perfect. So how can we fix these two tiny problems with space and time? And the answer is it's easy. Of course, when we evaluate it, we get out this thing which corresponds to the table we had before, and that's what we want to get. And notice that here, representing as data is fine because typically the answer is much smaller than the whole database. So that bit's okay. How can we fix the other problems? It's easy. All we need to do is write some bits in blue. So here it is with bits written in blue. And there are two changes. First of all, instead of letting DB be the actual type DB, this record type, it's an expr of that. Expr means this is a type already in F#. It's the type of quoted terms. What is a quoted term? It's just a data structure in the language, in particular, a parse tree that represents that term. And many languages have forms of quotation in them. In F#, the quotations are written using these brackets. So here's the open quotation bracket, blah, 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 and there's the closed quotation bracket. So I've got the same constructs that I've written before, but now written as a quotation. So the type is now an expr of what we returned before, and we've got this quotation. And indeed, when you, and then this here is an anti-quote, and it just means splice in the other thing. So that means literally you get database of people in both those places. So we're saying which database we're referring to, and of course, I'll get to that in a minute. But we only want to refer to one database, of course, so you should splice in the same one every time. And you can see that this has exactly the same structure as the SQL. So it's easy to run over this and generate the SQL. And then we'll send that off to the database, get the answer back. It'll be a small answer, so then it's easy to run over the answer and convert it to our programming language. So now this runs It doesn't read in the whole database, and it runs in the same amount of time as the SQL query, because the SQL query we're generating is exactly the same one that we saw before. So now we have a nice integration between our programming language and our database language. And how many people are familiar with LINQ? Right, so that stands for Language Integrated Query. It's a commercial product offered by Microsoft as part of the .NET framework, developed by Eric Meyer and many others at Microsoft, and it's based on exactly these ideas. So this is just another LINQ provider that we've given. And in fact, in LINQ, this is again very straightforward, but I'm going to show you some things that didn't work in previous versions of LINQ and do work in ours. But one thing you should take away here is, wait a minute, this idea of using quotation, it was already there in LINQ. There's nothing new about that. Right, that's why the title of this talk is Everything Old is New Again. It's a standard idea, and I'm just trying to draw people's attention to it again, and in part, draw attention to the fact that this is around a lot. So for instance, as well as in LINQ, you use pretty much these same techniques in Scala. So here's our naive query in Scala, written very similarly to what we had before. And in Scala, if you want to actually generate SQL, right, so this is the one that uses too much space and too much time. And if you don't want to use too much space and too much time, you just, before we wrote expr, in Scala you write rep, representation of. And rep is the same thing. It just means this is a parse tree that represents a term. And the type of the term is then what's written in the brackets. In this case, a list of records with name and age fields. And interestingly, right, Scala has very powerful type mechanisms. So in Scala, when you declare that the type is a rep, it infers that everything here is in blue. So you don't have explicit open quotation and close quotation. You don't have explicit anti-quotation, but the type inferencer works all that out for you. Cormac.
Just clarification. So the blue and the black are in the same language. Is that right? And is that
Yes.
necessary here?
It's not absolutely necessary, but typically when you use quotation in a particular language, you're quoting terms of the same language. You wouldn't have to. And indeed, that's an interesting idea. But the cases I'll look at, yes, we're quoting the same language. Yes?
Why do you still have the comma or the accent in your?
Why do I still have the prime there? That's a very good question. Why is there still a prime there? And the answer is it's a typo. My apologies. Thank you for pointing that out.
So that's something else you wouldn't do?
Indeed. Okay, so what does this run construct I showed you do? Right, you take the quoted expression, right, so you do all your splicing, you've got a quoted expression, you then simplify it. Now, the particular example that we had, no simplification is required, but we'll see that this simplify step or normalize step is very important. You then translate your query to SQL. You then run the SQL, right? You send it off to the database and run it. You get back a table, and you take that table and you translate it back into your host language. So those are the steps we saw. And then you get a theorem, some mathematics, right? Every run will generate exactly one query as long as the answer type is flat. That is, it's a list of record of scalars, where scalar is something like string or integer. It only uses permitted operations. So for instance, if you used is a prime, well, we can't translate that to SQL. If you use recursion for standard SQL, we can't translate that to SQL. So you have to only use the things that SQL knows about. And you should only refer to one database, right? If you tried to refer to two databases, you couldn't change it to a query on one database. Question?
So what if the answer was too big, that you don't want to bring it into memory, but you want to stream it one piece at a time?
Right, so what I said is what we're going to do is just take it and read it into memory, but of course you could stream it if you wanted to. But I'll leave that as an exercise for the reader. Okay, any other questions? You're asking excellent questions, thank you. Keep it up. Okay, so we've been through the Scala. Okay, so that's the basic idea. So any other questions about the basic idea? So now we're going to ramp it up and see more interesting things we can do. Okay, so here we go. So the first thing you need to be able to do is, of course, abstract over values. So yes, Julia.
So just a small question that's been bothering me. Why was DB in black? Does it mean that...
Oh, you mean here. Right, so you notice in front of it...
The next one, actually I was looking at the Scala one, but maybe it's the same answer, so go ahead.
It's the same answer for both. So dB is anti-quoted. Why is it anti-quoted? Because the type of the variable dB is it's an expr of dB, not a dB. So it's another parse tree that gets spliced in at that point. And exactly the same thing happened in the Scala.
Okay,
Good question. Thank you. So clearly we've got to be able to abstract over values. So we just do that. We write a lambda expression. So, sorry, a function abstraction. So fun is, of course, the way in which F# writes lambdas. So we have a function that takes two arguments, a and b, and then we iterate over all the people. And if a is smaller than w's age and w's age is less than b, then we yield the name. So these are the names of everybody whose age is between 30 and 40 in this case. And again, this would just translate very straightforwardly to this query. Note that here we are making use of simplification because the actual parameter 30 gets substituted for the formal parameter a, and similarly 40 gets substituted for b. So doing that simplification is part of what happens before we execute the query. So we build this big parse tree, which includes a function that's applied to something, and then we simplify that down to substitute actuals for formals, which, if you want the proper theoretical name, is called beta reduction. And we get that query out, and then we run it, and we'll find out whose age is between 30 and 40. So that's fairly straightforward. You should be able to do that in any DSL. But the following thing was very hard to do in many versions of LINQ, and there were long blog posts explaining how to do this. So now what we want to do is abstract not over values, but over predicates, over functions, higher order functions. So now we've got an expr that takes a predicate, a function from int to bool, and it returns a list of names. So here's our thing. So it's a function. It takes an argument p, which is our predicate. It loops w over people again. If p holds of w age, then we return the name. So here's a predicate that we can apply satisfies to. It's a function of x, which is true if 30 is less than or equal to x and x is less than 40. So in fact, after we do all the simplifying, so now we've got, here's our actual parameter. So we'll substitute that for our formal p. But now we have a function applied to w age. So again, we'll substitute out, and we'll replace x by w age. And now we've got 30 smaller than w age, and w age is smaller than 40. Oh, and that's exactly this query again. So it's the normalization that really makes this work. And that's the lesson I want you to take away. Normalization makes this stuff a lot simpler. And you might think, so let's see. I'll go off and do one more example.
So one question.
Yeah?
So normalization in this case would refer to the extraction of those conditions of the...
Normalization just means you have a function applied to some arguments, so you do the substitution.
Okay.
Now, much more interesting still is generating queries dynamically. So now I'm going to embed a little DSL using my little DSL. So here's a little DSL. It just expresses predicates. This one only has 3 constructs, but we could easily add more, being above a given number, age, below a given age, or both predicates holding. And then we can convert one of these data structures into an actual quoted term by saying, OK, above corresponds to the function of x that returns lift of a, above of a means that lift of a is smaller than x. Wait, why is there a lift of a there? Isn't it just a is smaller than x? Well, no. A is an integer, we're splicing something in here that has to be an expert of integer, so we need to convert our integer to the parse tree that represents that integer, and that's what lift does. Similarly with below, and then and is just a function of x that takes, again, takes this operation big P and applies what's big P of and of t and u. Well, it's big P of t and big P of u, and both of those are applied to our predicate, our argument x. So does x satisfy big P of t, and does x satisfy big P of u? And if it satisfies both, so we'll conjoin those together, then we'll return true. So this is fairly straightforward and simple code, right? There's only one problem with it. It's insane. Why is it insane? Because if we take a P and evaluate it, we get out this thing, which is unreadable. Actually, it's even less readable because I've subscripted x1 and x2, so you can see that those are different formal variables. Actually, it's all just x when you expand it out. But that's okay, because when we normalize it, we get back to that, and that's what we passed into satisfies before. So satisfies the P of this term just gets down to what we had before. Now, this is in quotes, and everything in the quotes is black. And you might think, what is quoted here? And the answer is the application term is quoted. So we're splicing in two things and then applying one to the other. And then this normalizes as before, and we get the same query as before. So for many years, it was mysterious to me. How do you use language-integrated query to generate queries dynamically? Because that's, of course, the interesting thing to do. But here it's just completely straightforward. And what makes it straightforward is that we have this insane middle step. But the insane middle step doesn't matter because it normalizes down. Wait, you'll say. That it'll take time to do that. That'll be costly. Well, no. It's very cheap compared to the cost of evaluating the query. So it's not really that big of a problem. Okay, so that's all there is to it. Now I want you to notice something that happened here. Here's the way we wrote big P. Right? This is exactly what we had on the previous slide. Many people in the real world don't do this. They do this instead. So instead of big P returning a function, the representation of a function from int to bool, it is a function that takes a representation of its argument and returns a representation of its result. And then it looks like this. And you notice if you did it this way, you wouldn't get all these functions applied to things that you then need to simplify. So this generates something more efficient. And this seems like a better idea. So why not use the one on the bottom? And the answer is, here's the satisfies that we wrote. But if we did it the other way around, we need to satisfies like this. And notice it's primed again. And what it does is it takes, our P now is a function from expr of int to expr of bool, not an expr of int to bool, like here. And that means to make it all work, we need to apply it to a quoted thing, and that's fine. We just apply it to wage, in quotes. And this all looks fine, except if you run it through F#, you get back an error message, which says, where is W bound? Because if you try to give this thing a type on its own, okay, well, its type is it's an expr of int, but its type should say, oh, and there's a free variable W. And there's no easy way to do that in the type system. So F# says, no, you're not allowed to use a free variable one place and bind it in a completely different quotation. And it gives you an error message that, loosely translated, is, what are you, crazy? And there's no way of making that work. So this is a perfectly fine idea, except it doesn't work in F#. Now, there are more complicated type systems for languages like meta-OCaml, where this does work perfectly well. And you can do this, and people do it. And then you might say, oh, okay, so as long as I'm using meta-OCaml, then I don't need the simplification. And in fact, for every single example I showed you, that's true. But if you go to my website and read the paper, which was published in ICFP 2013, it is filled with examples that don't work that way and where you still need to simplify. And indeed, I'm giving a talk continuing this one at DSLDI, Domain-Specific Language Design and Implementation, at 1610 in the room over there. And I'll give you an example there where you need to do simplifications that are not gotten for you automatically by meta-OCaml. So the meta-OCaml idea is a good idea as far as it goes, and it goes quite far, but you still need simplification.
Can you say again why that isn't going to work? Is it because you're quoted in one place and unquoted in the other?
Right, it doesn't work in F# because it doesn't let you have a free variable in a quotation. Every variable in a quotation must be bound somewhere in that quotation. This one is bound in a completely different quotation. So I was so used to doing things this way that I just thought we were doing things this way. I hadn't realized we were doing something that was different. And finally, I thought, wait, we're doing something different. There is a picture of me at the exact moment that I realized this. This is a recreation. But indeed, the exact moment I realized it, I was cycling in the links to work with Edinburgh Castle right next to me there like that. So what's the point here? This idea that's supported in meta-OCaml, where you can have a free variable in a quotation that's bound in a different quotation, is called open quotation. The only thing F# supports is closed quotation. So my point is, yes, this idea with open quotation is great, but as long as you're willing to normalize terms, and by the way, you might want to normalize terms anyway, then closed quotations work perfectly well. And the way of thinking of this is we want to use quotations of functions, something like x per a to b, rather than functions of quotations, something like x per a goes to x per b. Both of these are fine. My point is the QDSL technique involves the first of these, and it's an option you should consider. Maybe it works for you. Now, what we've used throughout this is Genson. So I mentioned Genson, right? I'm carrying him on my shirt. There's Gerhard Genson. Where does this come into it all? And you notice that he died at age 36, quite young. So here's natural deduction, as written out in Genson's original paper. This is a photocopy of his original paper. Some people said, oh, you shouldn't use that font. It's not my font. It's Genson's font. But this looks exactly like the way we do it now, except he wrote his A's and B's in German. Right? But the way we do it now is like this. This is exactly the same thing. These are his rules. And the key thing he worked out is that the rules come in pairs. So you have an introduction rule, which is called that because it has A implies B below the line. This says if assuming A, you can prove B, then you can conclude A implies B. And this is modus ponens. It says if you have a proof that A implies B, and you have a proof of A, you can conclude B. Similarly for conjunction. And the point is when the rules come in pairs, you can simplify. So here's a proof that A implies B, and here's a proof of A, and of course we conclude B. But we can conclude this much more directly, right? Because this said, assuming A, prove B. Well, we don't need to assume A. We've got a proof of A right here. So just copy in that proof of A everywhere the assumption was used. Of course, when you do that, you might make the proof larger, because maybe that assumption is used many times, and maybe this is a big proof. But you're making it simpler in the sense that this intermediate formula, A implies B, you get rid of it. So you're getting rid of an intermediate formula. And when you keep doing this, you get the following property. Here's what Genson said. Perhaps we may express the essential properties of such a normal proof by saying it is not roundabout. No concepts enter into the proof than those contained in its final result, and their use was therefore essential to the achievement of that result. So it says you can prove everything directly. Godkovitz did a lot of reformulation of this, and he called it the subformula principle. Every formula occurring in a normal form deduction, that's after we've done the simplification we talked about, in Genson's system of natural deduction of A from gamma. So A is our final conclusion. Gamma is a list of formulas, which are all hypotheses. So from some hypotheses, you prove a result. Then you know that every formula in the proof is a subformula of either the conclusion A or one of your hypotheses gamma. So we don't need anything else. Why is that relevant? This is exactly what we've been using, right? We wrote things with lots of higher order functions in them. Higher order functions, via the good old Curry-Howard isomorphism, higher order functions correspond exactly to implication. So if you can get rid of unneeded implications in a proof, you can get rid of higher order functions. And in particular, if none of your hypotheses, that is, none of your free variables, involves implication, and ours were all tables, which were flat, no functions, right? Just a record of lists of records of scalars. And if your result has no implication, ours was flat, it was a table, just a list of record of scalars, then we're guaranteed by doing normalization that we will get rid of all the functions, which is why it's easy to go to SQL. Those are the normalization rules. All I want to do is show you they're very well known and they fit easily on one slide. So here's your one-slide guide to doing your implementation. And this is actually useful in practice because in F# 2 and here are the different queries I showed you. I'll show some of those later. And some of them run in F# 2.0 and some run in F# 3.0, but thanks to our theorem, they all run in our version. Right? I'm told that they will be looking at applying these techniques when they do the next version of LI&Q. So that bit of theory gives you a nice bit of guide. So just to conclude, right, how does one integrate a domain-specific language and a host language? There are many ways of doing it. What I've shown you is a technique called QDSL. It's not a new technique. It's used in LI&Q. It's used in Scala. It's used many places. But the name, I think, helps to extract this idea as one of the things to keep in our toolbox. And what does it depend on? Two ideas: quotation, that's been widely known, and normalization. Going back to Genson, people often don't think about how important normalization can be. So go off and think of normalization and your friend, the fuzzy lambda. Thank you very much.
Thanks for the great talk. Some of it was over my head because I need to learn lots of these concepts, but forgive me for a perhaps stupid question. If I have a completely different domain that is not SQL, where recursion, for example, would be really interesting to have, would the same techniques still be applicable?
So that's not a stupid question at all. That's a brilliant question. I'll repeat the brilliant question. It was, well, okay, for SQL, you didn't have recursion. So, of course, when you normalize, the process terminates. If you have recursion and you try to normalize it, that could go on forever. What do you do then? So you notice that the theorem I gave said you're allowed some hypotheses. So what you can do is put recursion into one of those free variables. And I alluded to the fact that we've done feldspar. So in feldspar, you have a certain number of primitives that are not simplified. And these correspond to things that will compile into C. And one of them is called while. So we just translate the while into C. We don't simplify it, but nonetheless we can apply the subformula principle to guarantee that we get out first-order code. We can use functions as much as we want, and all the higher-order ones go away, and we're just represented with something that corresponds to first-order C. Now, in first-order C, the bound variables are themselves represented by functions, so it's a little bit trickier to do the proof, but it's not very tricky.
So to summarize, you provide not general recursion, you provide specific forms like loops, and then you make those usable.
Correct.
Thank you.
Good question. Thank you. And by the way, I will just put up this slide, right? You should know that this wasn't just done by me, it was done by me and many colleagues, and there are some of the relevant papers, and you can find those easily on my webpage. And I should also point to this, which is the repository that lives in the official F# project space, which is our library. So you can just download it and use it if you want to.
You said that there's only a subset of things that you can convert to SQL, like a supported set of operations. What if I want to write a function based on supported operations and use that in a quoted term?
Sorry, say that again?
What if I want to write my own function that uses supported operations only, and then use that in a
That
term?
works perfectly well in exactly the way that I showed you. So the question, sorry, I should repeat the question. The question was, okay, you can only use unsupported operations. Sorry, you can only, let me start over. You can only use supported operations, fair enough, but I want to define my own function in terms of those supported operations and then use that elsewhere. Can I do that? And the answer is yes. You would define the function as a quotation and just splice it in wherever you need it. And we saw lots of examples of functions that got spliced in. And the subformula property guarantees that all of those uses of functions will get normalized away.
We have time for one more quick one.
If I use an unsupported operation, will I find out at compile time or runtime?
Very good question. So one property that DSLs are supposed to have is that you find out at compile time if anything went wrong. Now, what we want to do in this example was just use bog standard F#. And in order to use bog standard F#, there are a few things that you need to check by hand. And I gave you the list. Right? I gave you the list of what they were. Is that within the quotations, your answer type is flat. That should be easy to check. That you only use permitted operations. Okay, that's pretty easy to check. And that you only refer to one database, which is, again, easy to check. A DSL diehard might say, no, I want the language to check that for me. Okay, then you have to write a little preprocessor that checks those things. So no, we don't do that for you automatically. If you wanted to do it, then you could easily write a preprocessor that does it, and then you have the cost of having a preprocessor. So it's a trade-off. But what we don't give you for free is detecting that you don't use unpermitted operations, where some other techniques for embedding do give you that for free. So indeed, you've isolated a cost, I would say a relatively modest one, of the technique. Right? I should say this is all early work. Right? I think this technique is worth looking at. I'm not going to say this is the way to do everything. What I'm going to say is this is worth looking at and evaluating and comparing to other techniques.
Okay, and that's all the time we have.
Is it? I thought we've got 10 minutes till the next session. Is that right?
No, the session ends at 20 after. So that you have time to go out and mill around.
That's fine by me, except I noticed that I didn't get started till a bit later because the previous session didn't start then. But that's fine. Thank you very much for your attention. I hope to talk to some of you over coffee. Thanks very much.